So today we will talk about process scheduling instead of read, copy, update, and hopefully we'll find it to be of benefit and help for your implementations as you go through the first Pintos project. OSs, of course, have a lot of resource management that they have to do, and the most important resource that OSs manage is actually the CPU. You're already getting quite a taste of that with the kernel thread implementation in Pintos and figuring out how to passively wait instead of actively wait, spin waiting, and also managing the ways that synchronization primitives interact and priorities interact and all that kind of stuff. It's a really good exercise, even though I'm sure it's very frustrating at times to try to figure out how to work through all of the various issues that come up. Of course, we want to have multiple concurrently executing processes. We've talked about this already for quite a few times. We've talked about the fact that almost always processes block on I/O, and while a process is blocked on I/O, we want to allow something else to proceed. That's just a smart way of using our compute hardware. And so you'll notice that processes fall into categories based on their state. We're going to talk a lot more about that today. Running processes are on a CPU. Ready processes don't have a CPU. The way that I describe it is a ready process is one that if it had a CPU, it could make progress. A blocked process shouldn't have a CPU because even if it had one, it couldn't make any progress. So the ready and running processes are really the ones that we care about with this question of scheduling. Block stuff is elsewhere. We move it into the ready queue when it's finally time to execute it. So the whole question of process scheduling is about how do we allocate CPU time to processes that can run. We want to make sure that when processes can run and we decide the CPU is now going to be available for some other process, that we pick the correct one to execute at that point. So you might remember this picture, which I like a lot. I hope you like it as much as I do. I think it just very succinctly captures the whole picture of process scheduling. So we create processes. The long-term scheduler, if we had one, the user plays this role now, governs when processes are introduced into the ready state from being created basically, and then they eventually get the CPU. They either get preempted and go back into the ready queue, or they may perform some task that blocks them, and so they end up on some blocked queue, and the medium-term scheduler is able to move them in and out of being scheduled, so that's why we have separate suspended queues. And the short-term scheduler, well, this is the one we really care about. The short-term scheduler is kind of the only scheduler we have nowadays on general-purpose computers because everybody has a computer. We don't do batch processing generally, and the user plays the role of the long-term and medium-term scheduler. Okay, and the kernel schedules kernel threads, not processes. This may seem a little weird, but in a real operating system implementation, as you all are noticing with like the little timer tick counter thing that the OS maintains, it's possible for the kernel to know exactly how many clocks a kernel thread has spent on a processor. So it can keep track of that. Not only that, but the kernel can also keep track of how much time the kernel thread has spent in user mode. Like when you trap back, or I should say you return from the trap handler or an interrupt handler back into the user program and you're running, and then you come back into the kernel on a trap or because of an interrupt, the OS can record that information as well. And so when you do something like time and then a program, and it prints that whole thing like real this many seconds, user this many seconds, sys this many seconds. It's because the kernel has all that information at hand. It's able to record that. And that allows it to make better scheduling decisions. Scheduling and context switching is performed at a single point in the OS kernel. And I want to mention, because there's definitely been a lot of great discussion about preemption, preemptive kernels. my previous slide about Pintos not being a preemptive kernel was wrong, as you can hopefully track through the information on Piazza and see how I reached the what I now believe to be a correct conclusion. Nonetheless, you'll still notice that there's always one place in the OS that takes care of the context switch. And so that's what we mean on the slide when we say that scheduling and context switching is always performed at a single point. You have a single function that gets invoked. The question of preemptive versus non-preemptive kernels is just what paths can lead to this call to the scheduler. And I believe in Pintos it's actually called schedule. So kernel threads see themselves entering schedule, and then they see themselves exiting schedule, but they have no conception of what happened in between. Okay, as I say here, kernel threads see themselves entering and exiting schedule, but in reality what happens is thread A comes into schedule, the scheduler runs, and then a context, and then thread B comes out. And eventually stuff happens and some other thread comes in and thread A comes out again because now it's thread A's turn. So thread A sees itself entering and then exiting schedule, but it doesn't realize that a big time gap may have occurred in between. So the schedule function does two things, which are both, I think, pretty evident. One is schedule has to figure out who should run next, who should get the CPU next. And then the second thing that schedule does is make sure to switch to that new kernel thread. Okay, that's easy enough. The second part of this scheduling operation where we're actually doing the context switch is handled by this thing called the dispatcher. And the dispatcher is the thing that saves the current machine context, including all of the registers, flags, all of that kind of state, and restoring the new thread's machine context so that it looks like the new thread is running instead of the old thread. Okay. Now this takes care of switching between kernel threads. Obviously, when we start to exit the kernel back to user mode, we may do additional things as well. So there's a number of phases of this, but the dispatcher is the thing that changes the machine context. Okay, the dispatcher is not useful work, putting air quotes around that. So it's not stuff that the user specifically cares about. So we want dispatching to be as fast and as efficient as possible because everybody will benefit if this is fast and efficient. Okay, now another thing that's a little bit surprising, and I would encourage you to look at thread switch. Oh, actually, I think I have it wrong. It's switch threads. You guys have probably seen all these things in Pintos, how I was talking to a student earlier today, and it was like init thread and thread init. It's like, okay, well, that's irritating to have such common names. But switch threads, you'll notice, has a current thread, it has a next thread, and then it also has this thread star that it returns. And it's like, why are there 3 threads involved in this? Well, the thing to remember is that switch threads is a beast that, when I'm calling it, I'm calling from a thread, and I'm going to start running a new thread. But then at some point, I'm going to switch back to the original caller, and I got to remember who I switched from in that context as well. So I switched from thread A to thread B, so the scheduler calls switch threads from A to B. And so that changes the machine context. And so the question is, when thread B starts running, what is it going to see? Because you're changing the machine context. Well, thread B, when it resumes running, will it see the arguments A and B passed to switch threads? And the answer is no. When switch threads actually switches to thread B, it's going to see the current thread is B, and the next thread is some other thread C. And so you can see in this picture that we've lost track of thread A. We've lost the fact that we're switching away from thread A because we've changed the machine context. And the machine context that was saved was the one where we were switching away from thread B. If this is bewildering, I get it. Just study it a little bit, and I think probably eventually it will make sense. So this is why we have a return value from switch threads, because basically the scheduler needs to keep track of the thread that was being switched away from. And this is another one of those magic functions that's implemented in assembly code. And the way that it works is that it sets up so that the return value from switch threads will be thread A, because that will be lost in the mix. And so that way, if thread A is actually terminating, or there's other resources that we need to clean up for thread A, or there's other details we need to track for thread A, well, the return value of switch threads will be the one we're switching away from. And therefore, the thread scheduler inside the kernel can take care of doing that final bookkeeping. Weird stuff when you start managing machine context, but it's so powerful. And I just think it's one of the coolest things that exists in computer science. Okay, so that's a little bit more detail about how that works. How do we pick a scheduling algorithm? How do we decide what it should optimize for? There's a lot of things that you can choose as measurements for what should be the thing that the scheduler cares about. We have CPU utilization. Are we maxing out the CPU utilization? Are we completing a certain number of processes in a given amount of time? How long does it take for a given process to finish, like measured by the wall clock? And we say wall clock because if you think about a process, it may spend a lot of its time waiting. Well, we don't really count that toward the process's execution time, but it's still time passing. So we call that wall clock time. Waiting time, how much time does a process spend waiting? Maybe we'd like to minimize the amount of time that processes spend waiting. And then also you can think about response time, and you can measure responsiveness in a number of different ways. And so different scheduling algorithms are going to optimize this picture in different ways based on the needs of the overall system. And that's why we have a bunch of different scheduling algorithms, because we may want to solve this problem differently for different kinds of systems. Think about your iPad or a tablet PC versus how a server that's serving tens of thousands of concurrent network connections might need different scheduling goals to do their jobs effectively. So you might remember that I was talking about sitting on the CPU, getting blocked on I/O, and then you're going and you're in a blocked queue, and then you become ready and you can run on the CPU. Turns out that this is a very common behavioral pattern for processes. And so you see on the slide I have here that a process will be running and it'll have these bursts of CPU utilization. How long is the CPU burst? Well, it depends on what the process is doing. And then we have I/O bursts in between. How long is the I/O burst? Depends on what the process is doing. If it's waiting for user interaction, the I/O burst could be very long, and the CPU burst may be very tiny. If we're doing some network operation, the CPU burst may be longer, and the I/O burst would be shorter than if we're waiting for the user. So there's a lot of different ways we can have this picture unfold, but generally it always follows this pattern. You have CPU bursts that are mostly short and a few longer bursts, unless it's really a compute-intensive process, but even compute-intensive processes will have longer and shorter CPU bursts. And of course, then you also have the question of how the scheduler manages processes. We may have a cooperative scheduler where the scheduler expects all the processes to be good citizens. Long CPU bursts are not interrupted. If they were interrupted, we would have preemptive scheduling. Okay, so you have this interesting thing. Do schedulers only do process switches at the end of CPU bursts, or can we say, okay, you've had enough time, we're going to interrupt you in the middle? And so that would be preemptive scheduling versus cooperative scheduling. And I'm really kind of surprised, and maybe you would be too, to know that many modern commercial operating systems, maybe I shouldn't use the term modern anymore, but many commercial operating systems were cooperative in their scheduling implementation for quite some time. Mac OS before OS X was cooperative. And Windows before Windows 95 was cooperative. And it's no surprise then that those operating systems would sometimes hang when a program was behaved badly. It was just the nature of the beast. But thankfully now, virtually all of the OSs that we use day to day are preemptive. Okay, simplest algorithm that you could possibly have is called first come, first serve, and you have all your processes in a FIFO, first in, first out queue. And so when you have a new process or a process that is yielded or becomes ready to run, it goes to the end of the FIFO and slowly makes its way to the front. And the process at the front is the next one that gets to run on the CPU. This is simple to build and is a very simple kind of mechanism. Okay, so yields are blocked. There's I was about to say three things and I hold up 4 fingers. There's 3 things that basically cause a process to get off the processor. If it yields, so it voluntarily relinquishes the CPU, it blocks on some long running task, or it terminates. One of those 3 things is going to be what gets the process off of the CPU, particularly in a cooperative type of scheduler. If it's a preemptive scheduler, then you can also have a timer tick that will kick it off the CPU. Okay, so first come, first serve, the way that we've described it is not preemptive. So what you see here is there are no priorities in how we make scheduling choices. It's just you get the CPU, you run. When you're done, you go to the back of the queue, you get back to the front of the queue, you get to run again. So this is kind of a very simple scheduling mechanism. You will sometimes see it in batch scheduling, but we have so few batch processing systems anymore that you see it exceedingly rarely. Now, what's interesting about this is if you add one simple ingredient, which is time-based preemption. So now we give every process a fixed amount of time to run on the CPU before they have to relinquish it. Now you have what we call round-robin scheduling. Okay, and so I believe this is what Pintos starts out with. Before you start doing the first project on Pintos, is it has a simple round robin scheduler, and then you build priority scheduling, and then you build the multi-level feedback queue scheduling mechanism, which is another kind of priority-based scheduling mechanism. So, you know, this is basically, you can see it's identical to first come, first serve, except now you have preemption on the CPU process. Okay. Now, what happens is as you increase the size or decrease the size of your time slice, you get different behaviors. If you have a large time slice, you're going to have fewer context switches. So compute-intensive processes will be happy. And you'll get a lot of work done because remember, context switching is overhead and we have less overhead because we're doing it less frequently. That's good, but then the problem is interactive processes will have to wait a long time to get the CPU when they become unblocked, and that will manifest as an unresponsive system. The user might press a key and then a half second later or a second later, the computer starts to respond. That's no bueno. People don't like that. So generally, round robin scheduling is terrible for interactivity and making sure that you have a responsive system for users. Now, shortest jobs first is another kind of scheduling mechanism, but shortest jobs first, we're kind of estimating or guesstimating how long the next CPU burst for a given process might be. And so let's say we have n processes and we guess how long the next CPU burst will be for each of those processes. And so when we're picking the next ready to run process to run, we pick the one with the shortest expected CPU burst time. That's what we mean by shortest job first. And what this does is it minimizes the average waiting time for a process to get to the CPU. I have here a couple of examples. 4 processes with varying CPU burst times, 2 units, 4 units, 5 units, and 7 units. And so you might have it unfold like this. the 2-unit process runs first. Let's assume that our estimates are correct, which is another great assumption, right? But so we go ahead and run our shortest process first, then the next shortest, and then so forth, okay? And if you do the math on this, you see that the average wait time is going to be 4.75 units of time, okay? And just as an example, you can see if we did the longest job first, 7542, then you're going to end up with an average wait time of 8.75 units. So shortest job first scheduling is a way of minimizing the average wait time. So if you have an interactive system, shortest job first is kind of the one that you'd like to go with, because then it will be very responsive. Typically, interactive processes have long I/O bursts and very short CPU bursts. Think about the way the text editor works that you use. You type a key, and the text editor updates the document, shows it on the screen, and then it goes back to waiting for a key again. So that's a very short CPU burst, which means it suggests that for good interactivity, we want it to be scheduled with a high priority. Okay. Yeah, so the hard part of shortest job first is guessing what the next CPU burst length will be for each process. And so we generally just predict it based on the previous behavior of the process. Generally, that's a great mechanism. A text editor is probably going to have the same behavior over the entirety of its execution in how long the CPU bursts are going to be. They'll vary, but they're not going to vary a huge amount. Okay. So a common approach is to use this thing called an exponential average, where basically you have the actual length of CPU burst n. So this is the most recent time. Remember how I was just saying that the kernel can know exactly how many ticks the program was on the CPU. And then we want to predict the next burst's length, tau, and we do it by saying, well, we're going to have this alpha. Alpha is basically how much we wait history, and how much we, how does this work again? I'm trying to remember. So alpha tau of n. So this is how much we, oh yeah, because we also have prediction. So we have T sub n, which is the actual measurement, and then this was the previous predicted burst. And so you can actually go through and expand this. And so you can see why this ends up being called an exponential average, because you at each point you have the exponent increases as you go back. And since alpha, 1 minus alpha and alpha are both less than 1, it ends up getting smaller and smaller. So further you go in history, the less it's weighted, and the closer you are to the immediate time, the more heavily it's weighted. And alpha allows you to tune how quickly or how slowly stuff falls off as it goes further and further into the past. So that's why it's called exponential average. Okay, this can be preemptive or non-preemptive. One of the things about it being preemptive is that you do have to worry a little bit about starvation, because you could imagine that if you have a short job and a longer job, the short job will run first, and then the longer job will get to run. But if new short jobs keep showing up and they keep jumping ahead of the longer job in the line, then it's going to eventually end up, the long job may never get the CPU. And that's a problem with scheduling. We want to make sure that everybody eventually gets the CPU at least a little bit. Okay, shortest job first scheduling. So we call this starvation. It's possible. So the way that we describe it is that there's no upper bound on the amount of waiting time for a particular process. All we're really saying when we say that is that we can't guarantee the process will get the CPU in any kind of reasonable time limit. Okay, so I already talked about this. Ready queue contains short jobs and long jobs. New short jobs keep showing up, and the long jobs just don't ever get to the front of the queue. There's various ways that you can deal with this. For example, you could have an additional priority mechanism that is used to also order the jobs in the queue and the long jobs. Like basically what you could do is the longer you sat in the queue, the higher the priority gets, so that the long job eventually gets to the front of the queue, even though it's not the shortest job first anymore. So so you can introduce little tweaks like that to get a scheduler to not starve long jobs or other low priority jobs. Okay, shortest job first is an example of priority scheduling. This is where we're saying basically the priority of a process is linked to the amount of CPU time we expect the process to take. So the lower the CPU burst length that we expect, the higher the priority. We can also assign fixed priorities, which is an interesting approach. Basically, we can assign it either an increasing number, so that like the larger the number, the higher the priority, or we could also do, a decreasing number is a higher priority. It just really depends on how the system is constructed. It's a convention. It's not really something that has to be one way or another. Okay. Priority scheduling can be preemptive or not preemptive. You can imagine that if a higher priority process shows up in the ready queue, we could either preempt the currently running process if it's a lower priority, or we could leave it on until it's finished doing its thing. Generally, we enforce preemption when we want to minimize the latency of high priority tasks. So if we want a system where if a high priority task can run, then we want the process that corresponds to that task to get the CPU immediately, then we preempt lower priority tasks. So you can see how all of these little things about bumping people off the CPU comes down to how responsive we want the system to be. How quickly do we want it to react to a change in circumstances that allows a given process to run? Normally in priority scheduling, and this is an unusual thing, when we're talking about fixed priorities, we don't generally impose a time limit on processes. So if you're high priority, you run, and the minute you block, that's when you actually relinquish the CPU. So remember, well, in this case, it wouldn't be yielding, it would be blocking or terminating is what would actually cause you to relinquish the CPU. So preemption tends not to be built into these systems except for lower priority process being preempted by a higher priority process. There's another couple of issues. One of these things is kind of cool. You're seeing the solution for it in the Pintos project, which is priority donation, because priority scheduling is actually susceptible to this issue called priority inversion. As it says here, starvation can be an issue. If you have a situation where higher priority processes are always able to run, then that can end up preventing low priority processes from running at all. And so you can do the same kind of little mechanism I described before. As a process has not gotten to run, you slowly increase its priority until it's able to run, and then it goes back to the old priority after it's run. And so then, it could slowly creep up again. You can do little tricks like that. And yeah, so this priority inversion thing is quite a significant issue. Basically, the concept behind priority scheduling is that a high priority process should always be able to preempt something lower priority in the system. But when you add resource locking to the mix, that's where you can start getting into issues of high priority processes that are actually blocked by other lower priority processes. The very most common scenario that's used to describe this is if you have a low priority process that's holding a lock on some resource, and then you have a high priority process that wants that resource, but the low priority process is holding it. Okay, so now the high priority process is blocked, and we resume running the low priority process. And if that was the only part of the picture, you're fine. The low priority process finishes, and then the high priority process gets to run. But unfortunately, if you have a third process in the mix that's a medium priority process, so it's higher than the low, and it doesn't need to do anything and it can run for a really long time, now you have, again, this situation where the amount of time it might take for the high priority process to get the CPU may become unbounded, i.e. the high priority process never gets to run, okay? And it turns out that you can construct this kind of picture with any number of processes. You don't need just 3. You could do it with 4, you could do it with 5, you could do it with 20, and it becomes a giant mess. And yeah, so as I say here, L is preempted by M, so it can never finish and release R so that H can resume execution. So the common example of this in real life was the Mars Pathfinder rover. I was telling a student about that earlier today in office hours. But the Mars Pathfinder had this exact situation occur. The high priority process was responsible for doing some critical system maintenance tasks. The low priority process was doing some low-level system coordination tasks that weren't very important. But both the high and the low priority processes shared a lock that they had to acquire. Then you had the medium priority process, which was either, I can't remember precisely the details, but either it was some radio uplink, so sending data back to Earth, that takes a while, turns out, or it was doing some climate measurements. I can't remember which was the thing that the medium priority process would do, but basically it would completely block out the functioning of the high priority process. And the result was that the Pathfinder rover kept resetting. It kept rebooting periodically. And, you know, it was a major issue. And the operating system implementation, as it was on the Mars rover, wasn't able to deal with this in the configuration that they'd sent it up with. Yeah, oh, I just told you all about it. So anyway, yeah, so this is the thing that I was talking about. The watchdog timer is a very common mechanism for resetting an embedded system that you can't be there to physically reset. You all probably have heard the stupid things about, oh, like my Windows computer isn't working right, so I just rebooted it and that fixed the problem or whatever. I mean, it's just kind of a common thing. It's not working right, so I'll reset it or I'll turn it off and turn it back on. So watchdog timer is kind of an automatic mechanism to do that. The timer counts down, and when it hits 0, the system is reset. Now that seems like a bad thing to have happen, but the way the system is supposed to work in normal operation is that you have something that resets the watchdog timer periodically. So you reset the watchdog timer and you keep resetting it so that it doesn't ever hit 0. Well, if it hits 0, the hardware is going to assume that the software has frozen, and so it'll reset the system. And so that's what the Pathfinder's high priority process was supposed to do, and it didn't. And so the thing kept resetting, and it was really irritating. Now, there are multiple solutions to this priority inversion issue. One is, I love this, the shotgun approach, which is just random boosting. So randomly, we will boost the priority of waiting processes to hope that the whole system is able to make progress. So I don't like arbitrary solutions because anything with random in it means that it's not really predictable how it will behave. Another approach is priority ceiling protocols, where basically you figure out for every lockable thing, what's the highest priority of the processes that can that can lock that resource. And then anytime a process acquires the resource, they automatically get the priority level of the highest priority thing that can access that lock. That's a nice, simple solution. I really like this approach, but it turns out to not be the most common approach. The most common one is some priority donation mechanism, where basically when two processes need the same resource, one is holding it and another is waiting for it, the waiter donates its priority to the process holding the resource. And so priority donation mechanisms are very, very common for solving this kind of problem. Now, you are seeing some of the challenges involved with priority donation. You may have long chains of processes that are blocked. I'm waiting on this guy's waiting on that guy's waiting on some other guy, that guy's waiting on, so you can end up having a really long sequence. So I have this example here. You can basically build this as long as you want, okay? So in this case, process 5 may need to donate priorities all the way through to process 1, okay? And so this, as an aside, is why Pathfinder in its initial configuration didn't have priority donation turned on, because the engineers looked at the problem and said, this may be an issue. We don't think it's an issue. We're not going to turn on priority donation because it's expensive. And the solution for Pathfinder was simple. It was to simply turn on priority donation in the kernel of the OS that the Pathfinder was running. But they didn't want to turn it on initially because priority donation is a somewhat expensive mechanism. Priority donation also fails badly with deadlock. If you have the whole thing of like two processes, each one holds a resource, and then each one tries to lock the other process's resource, well, if you have a priority donation issue, it's possible that your kernel can't properly handle cycles in the donation graph, and that can end up generating issues. So basically, the kernel has to be clever when it comes to process misbehavior. Isn't that always the case? The kernel needs to be hard. The kernel needs to be capable of dealing with any kind of mistakes or bad, broken process behavior that can occur. Okay, and then of course that's just going to increase the overhead of the donation implementation. Okay, I don't know if there's any questions about this. This is something all of you are implementing or will be implementing or have implemented. It's quite a clever mechanism. And I've definitely had students complain in past years, like, why would I ever build priority donation and priority scheduling? But it's a very common kind of approach in simpler embedded systems that have multiple processes or multiple threads. So it's a great thing to have seen. It's actually a very kind of fundamental approach to scheduling processes. So I'm glad that you guys get the opportunity to implement it. Okay, another scheduling algorithm to talk about is multi-level queue scheduling. This is akin to what you'll be building, but it's it has, I don't want to get ahead of myself. Basically, we notice that processes in a system, if you're running a general purpose computer, they have different characteristics. Like right now, I'm talking to my camera, and the camera has to stream data to my computer, and the computer has to periodically take the information and process it, prepare a stream, and send that out over the internet. And so that's something that's happening on a regular basis. So we say that it's a real-time scheduling consideration. I can move my mouse around, so now my mouse cursor is showing up. So PowerPoint has to react to my user input. And then there's also stuff going on in the background that none of us know about, like probably backing up to our network attached storage and so forth. So there's other things that are going on behind the scenes. So you notice that processes fall into general categories based on the things that they do. Okay. We may also notice that some are foreground because they need to respond to the user. And then you may have background processes that generally we don't care. We don't need to monitor them. They just do their thing. And so multi-level queue scheduling is a mechanism where we have different queues for different kinds of process behaviors. And each queue, besides representing a certain process behavior, also has a priority. And we assign processes to queues when they're initialized. We sort of know, let's say the process declares its behavior or something like that. And then we basically do round robin scheduling within each queue, but the queues themselves are prioritized. So we go from highest priority queue to the lowest priority queue. Okay. So we may have something like this. System processes, the highest, interactive, also high, interactive editing processes, lower priority. Like my Zoom feed is definitely higher priority than PowerPoint because it's more essential that Zoom get the processor on a regular basis than it is that PowerPoint reacts really quickly to me. It's like, it just isn't as high a priority. And then batch processes would be very low priority. Okay. So in general, if you are a ready process in a high priority queue, you always preempt somebody who is running or ready in a lower priority queue. Okay. And so then you use those queues to figure out who should get the processor next. Okay. There's other ways you can manage it. I'm not going to spend too much time talking about this because this is a fixed queue mechanism, and so it can't react when a process changes behavior. And that's one of the big limitations of this scheduling approach. Okay, you can see that queues can also have their own scheduling algorithms. That just makes sense. Maybe we do round robin on each queue, and each queue has a slightly different time slice. So the lower the priority, the larger the time slice we give it. That's a very common kind of approach with multi-level queue scheduling. Okay, so batch processes run with first come, first serve, or round robin with a large time slice, because remember, they will get preempted if something higher priority comes along, so it's okay to give them a large time slice. Other processes in higher queues might run with round robin scheduling. If you have real-time scheduling, you may have an OS. If it's clever, the OS will be careful to grant the CPU or accept the scheduling request only if it can actually meet all the requirements. It's possible to have a collection of real-time processes that's impossible to schedule. And a good OS will simply say, sorry, I can't schedule this. And it'll reject requests once it's unable to satisfy them. Okay. All right. Where we actually see this implemented is a variation of multi-level queue scheduling called multi-level feedback queue scheduling. This is the one that is super popular, and it's been used in most operating systems except for Linux. Linux has been on this wild different variation, which I'll talk about next time. And I think it's really worth considering because multi-level feedback queues were devised decades ago, and they've been used forever. And that doesn't mean they're the best. It just means they're good, and people haven't really spent time considering other options, except that the Linux developers definitely have. And so next time we'll spend some time talking about how Linux scheduling works. And there's some really neat techniques in there, so I can't wait to talk about that. Anyway, it is possible that a process's behavior changes, and really simple examples are all around, like MATLAB. I don't know how many of you use MATLAB for doing computations, but you're entering information for a while, so you are acting like an interactive process with short CPU bursts and long I/O bursts. And then you say, I want to start running this program. And so now MATLAB switches into being a compute-intensive program where you have very large CPU bursts and short I/O bursts. Same thing with Photoshop or any other program where you interact with it to set it up, and then you tell it to go, and now it just is going to sit on the CPU as much as it can because it has a lot of computation to do. So this is very common. So multi-level feedback queues allow the scheduler to adapt to the way a process is behaving. So instead of just having these priority queues of different kinds and then putting a process in a queue and leaving it there, now we can actually move processes between queues based on the observed behavior of the process. So as the goals here, favor short jobs because we're assuming that these are probably going to be interactive processes. So short CPU bursts, longer IO bursts. They relinquish the CPU regularly, so they almost never completely use their time slice. And we expect they should be high priority because we expect they're probably user interactive processes. We want to favor processes that frequently block an IO. So these are the kinds of things that we need to look for. And then, of course, we need to be able to adjust the categorization of processes based on the observed behavior, the behavior that the kernel observes of them. So we have multiple FIFOs or multiple queues in the scheduler, and each queue has its own priority. And the shorter the burst length and the more likely the process is to become blocked, the higher the priority is. And then if we have processes with very large CPU bursts, they end up being very low priority, and therefore they get preempted by other processes. Individual queues generally are scheduled with round robin, okay? So what happens is when a new process gets started, we go ahead and add it to the highest priority queue. Remember that queue has an associated time slice. Eventually it gets to run, and it runs and runs and runs, and then it gets preempted by the kernel because it's a short time slice. So now the kernel has to adjust the way that that process was categorized based on the fact that it was preempted. So like it says on the slide, if the process is preempted by the system, we move it down. We move it to the next lower queue because that has a slightly larger time slice, and it also has a slightly lower priority. Okay? If it yields or it blocks, then, if it yields, it'll stay in the same queue. If it blocks, then it goes into a block queue. But then when it comes back to the same ready queue. And then, it's sort of all the processes end up in queues whose time slice is slightly larger than the process's CPU burst length. And so that allows us to categorize the behavior of the scheduler and to categorize the processes based on their behaviors so that we can prioritize them effectively. Okay. And like I say on the slide, lower priority processes, if it was using very large CPU bursts and then suddenly starts blocking all the time, we can start migrating it back up through the queues because now we assume that it may be becoming interactive. Okay, let's see. There are a lot of ways in which these things can be designed because, of course, you can have different numbers of queues. You can have different algorithms for scheduling within a queue. You can have different time slice sizes. There's a lot of different ways that you can customize this. And so these have been used very heavily across most modern operating systems. Let me see if, so I have this on here. Windows, since Windows NT, basically would have 32 queues in the scheduler, and you can see that the higher the number, the higher the priority. Mac OS would have priority bands, okay? And I should probably update this. So this began with Mac OS X, but now we say Mac OS, now that we have Big Sur. And so that the bands basically were scheduled with separate algorithms, and threads and processes couldn't move outside of their bands. Then you have BSD, which would have various numbers of queues, and Solaris, which is a very old operating system that I would be surprised if you knew about it, but it's what Sun Microsystems wrote for their computers. I don't know that it's used particularly heavily anymore, but it also used multi-level feedback queues. Okay. Linux used something, it used multi-level feedback queues up until the 2.4 kernel, but then it changed its approach to something else. So that's multi-level feedback queues. You'll have to build something like this in Pintos, but one of the little secrets about the Pintos queue mechanism is that you don't need to actually have n queues in Pintos. And we encourage you not to. We encourage you to keep all the processes in one queue and sort them. That's actually the recommended implementation. So whereas a normal operating system might have n actual queues and move processes between them, in the Pintos implementation, we just expect you to have one queue and kind of keep things in sorted order. It's a bit easier to deal with. Okay, that's all we have for today. Next time, we'll cover real-time scheduling. There's some really fascinating results around real-time scheduling that I think hopefully you'll find as interesting as I find them. And then we'll also talk about how the O1 scheduler and the completely fair scheduler work in Linux. And they're very interesting, very different from the way that typical schedulers work. And, not to mention that they're probably the best names ever picked for schedulers. O1 and completely fair. Sounds like, oh, of course I want that. Anyway, I will hang out if anybody has any questions. Otherwise, I will see you on Wednesday.